Okay, we had one Blender assignment due and one programming assignment coming up, right? I wrote a bit of code for the other section, well actually for everyone, but I did it in the other section, about how to read a file, a model description file, and then generate a OBJ file based on that. So let me just talk a little bit about it before we go into our content today. The code itself is hosted on GitHub. I've posted a link to this resource in our classroom. So if you go into classroom.google.com and go into our class, this is where it is. See, it says Git repository for codes and other resources. There's a link right there. You can click here, or you can just go to github.com and then search for Spring 2018 CG as one word. That will take you to the same repository. Now right here, what we have is a OBJ generator. That's a NetBeans project. And what you can see over here, there's this models.txt file. It just says cube 15. So that's the target. You'd be reading a file like this where the model will be described in simple terms. We'll write the name of the model and then pass some parameters describing its length or the other aspects. For sphere, it might be the radius, it might be the number of segments and number of rings you have. For cube, we don't need much. It's the simplest of the tasks. That's why I did it to give you a demonstration. It says that we want to create a cube that has sides of length 15 each. Okay, now this is the input of the program, and let me show you what the output of the program may look like. So this is the output. Why do we have a V? I don't know. It's supposed to be O cube. Maybe I made a mistake in my code, or maybe I edited that by mistake. So if you look for the source itself, here's the OBJ generator, and actually it's better to open it with the IDE. Let me do that. So here's this generator. Okay, so it reads the model file. The way it's written, it reads the model file and it looks for the description of it. If the line that it starts with, if it starts with a cube, then it calls a method called generateCube. That's the one that I wrote. Okay, so if you're doing it for the sphere, if you're doing it for the cylinder, you need to write similar code. So if it starts with sphere, you're going to call another method, and you have to parse the parameters from there. For a cube, we only needed to get one number, that's the length of each side, and that's why we split the line into multiple tokens, okay, based on space. So this is how you do that. And the second token, token number 1, gives you the length. That's why we can get it from there. It's an integer length. So we can call this generateCube. The method is down here. And when you're going to write it for a sphere, you'd have to write a similar method yourself. So the heart of the code for this cube generation goes over here, generateCube. You give it a length, and it writes it out. But it writes it out as an OBJ file. The target is that you're going to read this OBJ file into Blender and load up the model. So right now I got this default Blender file, and if I go and file file import wavefront OBJ, And in my obj generator there is this output.obj. If I open this up, I get this file, this model. So it's a cube, and I purposefully left out two sides open just to show you that over here, if you notice, we are writing 4 faces. 1, 2, 3, 4, not 6 faces. That's why it has 2 open faces right there. Okay. So how do we do this? For a cube, it's really very simple. You're going to write the first line that you're going to describe that this object is a cube. So you write O for object, and then the name of the object. The name of the object is cube. In the obj file, we have a segment for the vertices where everything starts with a V, and we have a segment for faces. Every line starts with F's. So that's that. Now when it comes to the vertices, if you want to describe a cube that has length, let's say 15, as it is written in the output file, what's going to happen is that if you go to Blender, I think it's easier explained there. Okay, so when you look at this grid, we got a grid floor. I think the grid floor is on this layer. So let me go back there. Okay, so I got the grid floor back, and let me delete this. So by default, what you have is that all these grid lines, you can see that, I think, yeah. So these grid lines are all visible, right? They're all 1 unit apart. Okay, it's easy to measure that way. So if I want to create a cube, the default cube that you get, let me bring that in. The default cube that you get is actually 2 units long on each side. 1 over here and 1 over here. Okay, and that goes for all the axes. So for x-axis you have 1 in the positive side, 1 on the negative side. For the y-axis you have 1 over here, 1 over here. For the z-axis, 1 over here and 1 down here. Is this thing clear? Okay, so if I wanted to create a cube that's not of length 2 units, but of, let's say, 3 units, what am I supposed to do? I'd have to create a cube that spreads like 1.5 unit on the x-axis, 1.5 unit on the y-axis, negative x-axis. 1.5 over here, 1.5 over here. So that would allow us to draw a square, but since this is 3D, okay, since this is 3D, we'd have to take care of the z-axis as well. This got slanted, that was not what I meant it to be, but I think you got the point, right? Like if I can draw a square like that, with x and y axis, I can also create a square in this pattern in x z axis, and both of them combined together will form the basis of a cube like this. So all I need to do is to find out the corner points, the 8 corner points over here, and 4 back there, and once I have the vertices, I can join them by faces. Okay, so if they were 1 unit on each side, the coordinates would be something like 1, 1, 1. For the positive one, I shouldn't be writing that. The positive ones are over here. So 1, 1, 1 actually is this one. This one right here, that's going to be 1, 1, 1. Okay, if you go on the left side, that's going to be minus 1, 1, 1. Something like this. So right here, what I did is, as soon as you get the length, you can divide that by 2, because it's going to be, half of it is going to be on the positive side, half of it is going to be on the negative side, and that way you can generate all these 8 vertices. Like if you can get the first 4, then you can just copy paste that and change the z-axis. You can keep one of these axes fixed. For example, the one that I have over here, it has negative y over here, and then I switch the y values over here. they're all positive-wise, but the same pattern remains. The actual task, once you have them ready, is to join them together, and that's where you need to find out, like you can draw it on a piece of paper, you can label them, and then join them accordingly, right? Let's say, let me do this over here, it's easier done on journal. So what I'm trying to say is that, let's say we draw a square like this on the front, another square at the back, something like this, and then we can, well, not even a square. I mean, I wanted to go with points rather. So let's say I got 4 points on the front plane, and I got 4 points back here in the back plane. It doesn't look like a cube yet, but you can number them. You can number them like 1, 2, 3, and 4, and then 5, 6, 7, and 8. Okay, so that tells you now that if you want to make a cube out of it, you need to join the faces. So one of these faces can be 1, 2, 3, and 4. Once you join them together, you have a face. So that's why you need to write a line like if 1, 2, 3, 4. Over here, you have another one, 5, 6, 7, 8, but that's the back face. So if you do it counterclockwise on this side, that's going to be wrong. It has to be clockwise because that's the other one. You see over here 1, 2, 3, 4. This one makes sense because you're going in counterclockwise. 1, 2, 3, 4. If you go 5, 6, 7, and 8, that's going to be wrong because that's going to be the internal face inside the cube, but you want it to be on the outside. So what I mean by that, if you're looking from this angle, if I go counterclockwise over here, I get this direction right, but I can't do it this way for this face. Okay, it has to be exactly the other way around. So that's when you'd say that this can be 8, 7, 6, and 5. 8, 7, 6, and 5. Okay, and also now 1, 5, 6, and 2 would make a face. This one over here. 1, 5, 6, and 7, and that's also counterclockwise, so that the normal sticks out. If you're going to do it for the top face, 3, 2, 6, and 7 can be one of them. So you just figure that out and then write down the face, the vertex numbers in the faces in this way, and it would come out right. Okay. So in the other section, you can watch their video. I actually did it for 6 of those faces. Okay. See if that makes sense, and if there's anything wrong, you can fix that there. There are 2 faces left there, you need to fix them as well, so that's another thing. Now it's going to be more of a challenge if you're going to deal with cylinders, if you're going to deal with spheres. Okay, what you need to understand that it's much easier done if you're familiar with something called polar coordinates. You need to map polar coordinates into Cartesian coordinates. We are more familiar with Cartesian coordinates, most of us, but they're the same thing, right? I mean, any point on a 2D plane can be described with the polar coordinates and also with Cartesian coordinates. No big deal. why polar coordinates are good over here is, let's say I want to draw a cylinder like this. Okay. So in order to draw a cylinder like that, if you try to do it in Blender, let us just have a quick look at this thing. That if I insert a cylinder, it's actually made out of a polygon mesh. So there are a lot of polygons that make up this thing. And let me reduce the number of vertices over here. Let us go with 16 or even less. Let's say 8. So it doesn't look circular anymore. And if I drop it down to, let's say 4, it looks like a cube now, but it's actually a cylinder. Okay, it's like an elongated cube. If you make a cross section over here, then we'll have two cubes over here. So the idea is that as you keep on increasing the number of vertices, you'd see that it's going to turn into something circular and it's going to look like a cylinder. We have seen this before. Now the challenge right here is to generate these vertices. So let's say we got 5. Okay, and let us look at the top view. How can you generate these 5 vertices? So let me rotate this for ease of calculation, like so. Now what I want you to realize is that this thing, the first vertex over here, can be aligned with the x-axis. So if this is the origin and this is vertex number 1, OV1, that will be along the x-axis. If you're looking at V2 or V3, they will each create equal angle with the center right here. Since this has 5 vertices, it will create 5 separate angles, and each of them will be equal to how much? Theta equal to? Oh, where's my calculator? Divided by 5, that's 72. Yes, I mean, that's what you guys were saying. So we know that this is going to be 72 degrees. So instead of 5 vertices, if I give you 50 vertices, it's no big deal. It's going to be 7.2 degrees. How do we know that? 360 divided by 50. So depending on the number of vertices, you can calculate what's going to be the internal angle, right? Now, what do we need to do with this? We need to calculate the coordinates. Okay, so instead of saying V1, V2, V3, and V4, we can say that they are VIs, some vertex I. How many vertices we got? 5. So I can be 0, 1, 2, 3, 4. Okay, instead of saying 1, 2, 3, 4, let us go with 0, 1, 2, 3, 4. That's actually easier, and that's going to help us write them down in proper manner as well. So over here, let's say I is equal to 0 to 4. Now what's going to be the angle for each of them? What I can say is that the angle will be I times 360 divided by 5. Can I say this? When I is equal to 0, the angle is actually 0, because this is 0 times 360 by 5. When I is equal to 1, then we have 1 times 360 by 5, that's 72. When I is equal to 2, up here, that's 2 times 360 divided by 5, which is 144. And so it goes, right? So what I did right there is now we can calculate the total angle just like that. For any vertex, we can calculate the total angle it makes with the x-axis. Is this thing clear? So does that help us in finding out what's the x value and what's the y value? Do we know that? Turns out we do. Because if you look at a right-angled triangle like this, let's say we got theta over here, and let me write the labels. Let's say this is the perpendicular P, this is the base, and this is the hypotenuse. So right over here we can say this cos theta is equal to B by H, and sin theta is equal to P by H. Okay, now if you look at this thing, this is actually aligned with the y-axis over here. This is the y-axis, and this over here is the x-axis. So for any vertex vi, if I want to know the x-intercept over here, that's actually B. And if I want to know the y-intercept, this part, that's P. Or in other words, this is going to be H cos theta is equal to our x coordinate, and H sin theta that's going to be our y coordinate. So if you do a multiplication, so P equal to sin theta, that means the y value, and B equal to H cos theta, that's the x value. So with that knowledge, you can plug that back over here to get the x value. How do we get this? If this is the radius, x equal to r cos this thing, because that's the theta. So x is equal to r cos I times 360 divided by 5, or the number of vertices n. Okay, that gives you the x coordinate. If I wanted to find out the y coordinate, it's just as simple. What would that be? I wrote it for x, right? So what's it going to be for y? R sine I times 360 divided by n, the number of vertices. Now, if you're going to do calculation in Java with sine and cos, you'd have to do it with radian, not with degrees. Okay, so you're not going to write 360 up here. Instead of 360, we are going to replace that with 2 pi. And in Java, we write that as 2 into math dot pi. Okay, so that's that. If you put that in, you're going to generate the x and y coordinates. That would give you, let's say, one such plane. Okay, you can generate all these vertices, and you can write down the vertex numbers that would create a circle like that. And you can also do it for, if you do it for the bottom half, you can also do it for the top half. The fun part is to join these things together. You need to figure out which vertices they are, and let me show you how this is done. Let's say this is 1, 2, 3, and 4, and 5. We got 5 vertices over here, and these vertices now will be what? 6, 7, 8, 9, and 10, which is kind of obvious, right? But this 6 is actually 1 plus n. N is the number of vertices. This 7 is actually 2 plus n. So if you want to draw this plane or this face, what am I doing? This is if 1, 2, 7 and 6, right? This is 1, 2, 7 and 6. But if I'm writing a for loop, then I'll be changing these values. Right now this is 1, 2, 7, 6. The next time it's going to be 2, 3, 8 and 7. Okay, it's going to change. And then it's going to be 3, 4, 9 and 8. So we need to write it in a for loop style or any sort of loop style. So we need to be able to change them somehow. So if this is I, this is going to be I plus 1. How about this? This is going to be I plus n plus 1. And this one up here, I plus n plus 2. Or maybe I made a, actually this is I plus n plus 2 and this is I plus n plus 1. So you just figured that out. Alright, so if you keep on changing I, then all these vertex labels can be auto-generated, and the vertices themselves you have already generated and written them down with V lines. These would be the F lines, and altogether if you can write them into a file, you can see that back in Blender. So the easiest way to go about generating these things is to go part by part. So if I were you, I wouldn't try to draw the whole cylinder at once. I'd try to see if I can do the bottom plate, and if that's done, can I do the top plate? Can I have two plates like this? Then can I join a few of these faces? Maybe I'd write them down in a hard-coded style, not with a for loop first, to see if I got it right. And then if I can get that idea, then I'd change that into labels like this with I, and then run a for loop. So that would be it. The task itself is not too difficult, it's just to get it right. And I gave a hint in the other section for the most challenging task of these lot. Like I gave you 4 things, and the most challenging one is the helix. Okay, so what I told them is to look for helix parametric equation. Okay, and here's a very nice site, Math World Wolfram. You'll have a lot of math resources from there. So this thing is a parametric curve. As you keep on changing t can be the angle. If you keep on changing t, you can generate the coordinates for x and y, and also for z, where c is another parameter that would define the springiness. Okay, if you have a low value for c, then it's going to be shrunk down. If you have a high value, then the spring will be really stretched. Okay, so you can take these things as parameters from the user, that give me the value for r, give me the value for c, and based on that I can generate a helix. What you need to understand is that you're not just drawing a curve like this. You'd be generating a mesh. Okay, the difference can be seen over here. Let's see, if I ask you to draw a circle, that's going to be something like this. But I'm not asking you to draw a circle. What I'm asking you to draw is something like a torus that would be built on top of the circle. So if you have a circle and you can draw many circles around it like this, you can then join those circles together to form this tube. So when I say that draw a helix, okay, you're not going to draw the simple curve like this. What you're going to do is you're going to draw circles in here so that they can form a tube-like pattern that moves up like a spring. That's how you'd visualize that. Is this thing clear? Alright then, so that's with the programming task. The Blender task, that was simple, and I think most of you submitted that already. I'll go through your work and give some sort of feedback. Okay, anything about this assignment or anything else for that matter? No? Okay, so let us start today's class then. Okay. What I intend to do in today's class is to go through a full example of how we can calculate form reflection for any given vertex. Okay. And for that we need to have some sort of setup, a real life scenario. We have a particular model, we have defined a material, and we have a certain lighting condition. Based on that, we want to find the color or the intensity of one particular vertex. Okay. And when I talk about the intensity, it can be the red intensity, it can be the green intensity, it can be the blue intensity. We need to find those out separately. Okay. So we'll be talking about one such thing. And in our previous class, I had this thing. Where's this? Where's our classroom? One step back, I think. Well, not even here. Oh, this one's over here. So that's the classroom. Over here, I posted a link that we can get the ambient, diffuse, and specular values for known materials, like these are over here. So let us say I want to create a golden monkey. Okay, so in Blender, we can get a monkey head for free. It's right here. Okay, so you can go into the Create tab and get a monkey right there, or the shortcut that I use is Shift A, that brings out this Add menu, and you can get the monkey from there as well. Mesh and then monkey. I want it to look smooth, so I'm going to enable smooth shading. And also, I will add a subdivision surface modifier to make it even smoother. This actually increases the geometry, as we discussed before. So you can see that we have more faces now. If we go for the actual render, I mean, it's written up here, we got 7,872 faces. So if I hit render right now, it's really not a great setup. We don't even have the material defined. It doesn't look like a golden monkey. That's what I meant. Okay. We have a lamp over here that's at a bad angle for us because we don't see everything lit. So I'd like to move this thing to a point where it actually gives more light to the monkey's face. And maybe that's a slightly better setup. Although, like these parts, they don't catch light, that's why they're in total darkness. Okay? So there are quite a few key elements missing, right? We don't have light coming from an unknown source. The ambient light is totally missing, because if it were there, then this part wouldn't be in total darkness. There would be some sort of light. Even if very low amount of light, there would be very subtle amount of light in here. We don't see that. Okay, so we need to account for that somehow. We need to bring in some sort of ambient light, and we also need to define the diffuse and specular component over here. So how we are going to do this? We have done this before. We go into the material and we create a new one. Let's say this is going to be called monkey body. Or actually, this is for the monkey head. Why do I say body? Okay, so we're going to define this material. And over here it says diffuse, and we can put a color over here. Let's see how we can use this value. So this is for the diffuse column, right? 0.75164, that's the red. 0.60648, that's the green. And this one's for the blue. So I can copy these values, go into the diffuse, This is going to be for the red, so I can paste it over here. That's green. So I can change the green value, and I can also change the blue value. So already it started to look like golden, right? So that's one part. We can also push up the intensity so that it takes the full color. And if I lower the intensity, maybe it's going to be like it's old gold material that has lost its shine. And if we polish it again, maybe it's going to become shiny like this. Okay. So this is in our control. This is not done yet. Okay. Why is it not done? Because we have only covered the diffuse part. We haven't handled the specular one. It's very similar. You copy the specular part right in here. Okay, so that's the specular light, and let us give it full intensity for now. The hardness or the shininess is this factor. Okay, so this is how maybe a very polished gold would look like. I mean, this is a bit too much, and the hardness over here, which is what we are using for shininess, is not really scaled up for this. Okay, if you look at all these values, you'd see that they range from 0 to maybe 1. But over here we were dealing with some integer scale. So that's why you need to account for that, and maybe get a feel of what your eye feels is the right amount of shininess for a golden material and settle for that. It would be nice if we could use this thing, but they conform to a different range. They're not in the same range. That's what I'm saying. Maybe they're in the range 1 to 255 over here, although you can go higher than that. But over here, they're in the range from 0 to 1. That's why you need to scale it up, or scale it up definitely to a certain level. So let's say maybe this is my golden monkey head right now. What I didn't account for is the ambient component. Okay. So right now if I render this is how it looks like, but now some part of it is in total darkness. The ambient reflection, as you'd notice, there is no easy way to set up the ambient color, the ambient reflection color. What Blender has, this is due to Blender Render, it's a render engine. It doesn't let you control this ambient so much. We have the ambient component. It says how much of ambient light is going to reflect. It's going to be white ambient. So if you decrease the value, it's just going to change the scale of it, not the color. So let me zoom it up and show you what we have in here. On this side, if you come down, see this ambient value, yes, you can lower it. Okay, but it's not going to change the render in anyhow because we haven't set up ambient light yet. And also, the fact is that it doesn't let you choose a color. So, if you go back to this table, you see we need 3 different parameters, red, green, and blue for the ambient. We just don't have that over here in this particular setup. So for now, for just the sake of it, let me just enable ambient light and let us leave it at, let's say, 0.7. Okay, we cannot control the red, green, and blue in this setup. It's not built for that. If you have a ray tracing engine, then you can set up ambient light and you can do that. What Blender does provide you is you can actually render the world, and through that you can control the ambient color. So right now you see that this is in total darkness, but you can, if you go to the World tab, it's up here. Okay, here's the Material tab, here's the Modifier tab, and here is the World tab. Right here, there is an option Let me zoom it up so that you can see it better. Okay. There is an option to define the ambient color. So what do we see right now? Yeah, it's set to 0, so it's totally black, and that's why you see that nothing's getting reflected. Okay, so but we can bump it up. Okay. Do we see the difference? No, we don't. Yeah, sorry. It's zoomed up too much. So let me try again. For the ambient color, if we lower it, it gets darker. So I mean, this is like a added color for the entire thing. I mean, you don't want to push it high because that makes everything go bright. Okay, but this is where you can actually play with the color itself and say that the ambient color will be something like that. So if you put that in, see how that changes everything right here. Okay, so the way they have set up this ambient color, it's more about the environment altogether. You can define it for as an additional light source that gives a very little amount of light, but it's coming from everywhere. That extra bit of dark brown thing is actually added all over this monkey's head. It's not coming from one particular source. But for the diffuse light, yes, it does have a sense of direction. We know that the light is coming from here, somewhere over here, because that's where the brightest part is. And as you go further away, it gets darker. That's what we studied with the diffuse light. As the angle with the surface normal increases, the amount of light reflected will be decreased. Is this thing clear? So based on this certain setup, right, let us go with a little bit less. Okay, so here we have this ambient light, a very little amount of ambient light, and we have a light source somewhere. We have a light source over here, and that would also play its part. And based on this light source, this is how it looks like. But if you change this light source, so we get a color of this light source, right? That's white. But if I use a blue light, for example, it doesn't look yellow, it looks greenish, because I'm mixing blue with yellow. That altogether makes it greenish tint. Do we see the change? Or if I turn it towards red, or let's say even a little bit brown, the color also changes. So it's not just the material itself, it's also about the color of the light source, that we will see a certain material in a different light. Okay, so whatever be it, let us leave it at that we got this this light source defined, and we're going to calculate the color of a certain vertex. Okay, this is the final output that we see, and we need to find out what's going to be the color of a certain pixel. We will talk about the pixel level in a bit, but see, all these pixels are here, and we want to find that. But before we get to the pixels, we need to be able to identify at least the vertices. So let's say I want to find out the color of this particular vertex, this one right here. And in order to do that, first of all, I need to identify a face, and I need to identify the vertex normal. And let us have a quick look at this somewhere over here. See, the vertex normal is pointing this way. This vertex normal over here is pointing this way, and we have vertex normal all over here. What I'm going to do though is I will consider this to be flat shaded initially, just for the sake of simplicity, and we'll say that whatever the face says, I'm going to go with that. So I'll say that this is the surface normal on that particular surface. So if you look at this tissue paper box, we have 4 different vertices. Okay, they will have 4 different surface normals, but what we would assume initially is that they will have the same surface normal. Okay. If it's a curved surface, they can have different surface normal for different vertices, but the trick is, I talked about it in terms of smooth shading, that you can calculate the surface normal on the different faces, and for the common vertex you can use the average surface normal. That makes it smooth. We talked about faking it. So yeah, if you're talking about this particular vertex now, well, that got shifted as I was moving this thing away. So let me delete that. I want to find out the surface normal over here, because from some light source, the light ray falls down over here, gets reflected, and we need to calculate what's going to be the color. Is this problem clear? This thing, that like what our task is right now, is this thing clear? That here is a point P, I want to find out what's the intensity of this point. And when I say intensity, I really mean 3 things. The RGB. So we are going to calculate the IR, IG and IB separately, but in class it's going to take time, so I'm not going to go through all of them. I'll probably just do IR or IG. But if I give a different thing in the exam, it's no big deal. It's the same thing. You just have to work for the right channel. Okay. So there are multiple parts to solving this problem. First of all, we are not given the surface normal, and the surface normal is really very crucial, because without the surface normal you cannot calculate the diffuse light, the diffuse reflection. So just to recall things, the stuff that we need for today's task, the formulas that we need, let us identify them. Let's say I want to calculate the surface intensity, okay, and this is actually IR, IG and IB. You're going to get a color. What's the intensity of that? And if you just consider them to be channel, so if we talk about one particular channel, it's going to be the similar thing for other channels. So in that way we can drop these things. We can drop IR, IG and IB. What we figured out in our previous discussion is that if you're going to calculate the ambient reflection, because the entire formula stands on this, I equal to IA, intensity of ambient reflection, intensity of diffuse reflection, and intensity of specular reflection. We have covered each of them. Okay, we have developed formula for each of these things, and everything combined, if you add them up, you get the total reflection right here. So what did we write for ambient reflection? Intensity of the light source times rho A, where rho A is the coefficient of ambient reflection. It's a constant value, how much ambient light is going to get reflected. We also had another formula, ID equal to IS times rho D times max of L dot N, where L is the vector that goes to the light source, N is the surface normal, divided by magnitude of L, magnitude of N, and 0. Okay. We also had ISP, which we did in our last class. It goes something like this. I mean, this part is pretty much common. Intensity of the light source multiplied by how much specular light is going to reflect. That's rho SP. Multiplied by, this is where we have a new vector, the reflection vector and the viewer vector. So we need to keep that in mind. So we have, let's say, max of reflection vector times the viewer vector divided by magnitude of R, magnitude of V. That gives you the cos phi. And now you raise that to the power f, where f is the shininess factor. Tells you what type of material it is, how much shiny it is. Okay? So altogether, you need to work with all of them depending on what's asked for you in the exam. And if you're going to write a computer program that generates a picture for you, you're going to implement all of them, no question asked. I mean, it has to have all these components. But in the exam, I can't really ask you to do all these things because it takes time. As you'd see when we are going through these things, it takes quite a bit of time to set it up. So usually I don't ask for every one of them. Maybe sometimes I ask to find out the reflection vector, not even this calculation. Sometimes I ask for the diffuse calculation. So I'll ask part of the problem, not the entire thing. Okay. The entire thing itself may take like an hour or so, depending on how many information you got. So we need to calculate all these things, and just to give you an example of how it can be like, let us say that we want to find out IDG. What would that be? Intensity of diffuse reflection for the green channel. Is that clear? So what are the things we need over here in order to find that out? We need to find out intensity of the light source, and intensity of the light source has many different channels, 3 different channels. Okay, so what we are really interested to find out is ISG. Multiplied with that, you're going to throw in rho what? DG. Multiplied with that, you have max of this thing. Are we going to put G in here? LG, NG? No. It doesn't really depend on the color channel. The vectors, they're not really dependent on the color channel, not at all. So they will be just as they are, without any change. So I can put that right in here. Okay, so altogether, this is what we got. IDG equal to this thing, and we need to figure out these values one at a time. So help me out. How can I find out ISG? If you get this problem in your exam, I can't give you a computer with Blender on it. The question itself will have all the narration. But right now, if you look at this setup, to find out the ISG value, we have to look into the lamp. Okay? The lamp gives us a color, and right in the green value, this is the green intensity of the light source, that's 0.479. ISG will be 0.479. That's how we know that. Because it's not a white light, it's a colored light. So it has different components, red, green, and blue. And since we are calculating the value for the green channel, this is what we need to worry about. The red and blue, they can stay as it is for now. So it's just 0.479. It's not anything less or anything more, because we're not tweaking with the energy value. If you lower the energy value, you'd have to multiply it with that factor. If you increase the energy value, you're going to multiply that. So for example, just to show you what I mean, if I had energy equal to 0.8, the light will be darker, right? It will have less energy. So then I'd have to write ISG equal to 0.479 times 0.8, because we are going to lower the energy. If you're going to increase the energy, then yes, you're going to bump it up. Right now, since this is given as 1, we're multiplying with 1 and nothing changes. 0.479. And just for completeness, I'm going to write it with multiplied by 1. That's this part. Is this thing clear? Rho dg, how do I find this value? It's given over here. We have a gold material. Rho dg is over here. 0.606, that's the value. Okay, that's the diffuse reflection, and that's for the green channel. So right in here, let us throw in 0.606. Now what do we do with the rest? We got max of L dot n divided by the magnitude of L divided by the magnitude of n. Okay? Now this is where we get stuck, because we don't have the value for the n vector. Okay? Do we have the value for the L vector? We got both of them, but we need to find that out. So first of all, if you look at this thing, this vertex P, we have certain coordinates, right? So let me write them down. We have x value, y value, and z value. So this is a point P equal to, this is the x coordinate, here's the y coordinate, and we got the z coordinate, that's the point. We have another point where the light source is, and it's up here. It's also in the same 3D world. So the scenario is that we have a point P over here, we have a point L over here, and the L vector is actually the vector that goes from P to L. How do we find that out? How do we write this? L equal to thank you, L equal to L minus P. Okay, so now we need to know the coordinate of L, and that's given over here. So why not put that in? That's that. Okay, so we got that. So now we can write the L vector as L minus P. This is going to be a vector. It would have 3 different components, and it's probably easier done with a spreadsheet, so give me a little bit of time. I don't want to do it by hand. So copy that and also copy this. So I'm just writing them down, and I'm going to subtract from here this point. Okay, that gives us these values. The coefficient for I hat, j hat, and k hat. And can I copy from here? Maybe I can. Yeah, it works. So what we have right now is this L vector. This is the L vector. Do we know the N vector? Right now we don't. Okay? But it's not too difficult to find out this vector. In order to do this, let's say this is our point P. We need two other points and then calculate that. If we can define a vector A that goes this way, if we can find a vector B that goes this way, we can do a cross product to find out N. Okay? Let me just save this blend file. Okay, so what's the value of A? How do we find this out? We have P, and let me write some labels. Let's say we have another vertex Q, another vertex R, P, Q, R. How do you find Q? Just take your mouse pointer there and you can look up the values. Right? The X, Y, and Z coordinates are over here. So we can simply copy that. And let me copy it over here because that's a little bit easier to manage. Over here we had L and we had P. What we did to find out the L vector is L minus P. So right now let's say we have a point Q. Okay, so what's the value for point Q? That's the X coordinate and this is the Y coordinate. And where's my Z coordinate? It's right here. Okay, so we got the X, Y, and Z values. Let me make them a little bit smaller. Also, I don't need that many digits after the dot. So something like 4 digits after the dot would be enough. Okay. So this is actually the X coordinate, this is the Y coordinate, and this is the Z coordinate, as you can see. Now we have the Q vertex. Can we find the A vector? How do we find the A vector? It's the other way around. It's Q minus P. Because the vector goes from P to Q, so it's going to be Q minus P. Q minus P. Okay, so that's that. We got our A vector. So let me copy this and write it down. Right over here, this A vector is going to be Q minus P is equal to this. Let me save this somewhere so that I don't lose this altogether. Okay, so we got q minus p, and now for the other vector, that's the b vector, how do we find that out? Just a bit. Hello. Welcome, sir. Any classes? So for the b vector, we have a vertex up there that's r, and over here we got p. How can we calculate that? The b vector, r minus p. It's as simple as that. Okay, and in order to find out the coordinates for r, you just take your mouse pointer there and you can copy the values. So let me just steal them. So that's one. And over here, that's the other one. And down here we got this. So this is our r, and now we need to find out this thing. R minus p. R minus p gives us our b vector. So let us write that down. Somewhere over here, we got r minus p equal to this. See, in the exam, you don't have to do that much. I mean, everything will be given to you. You need to understand what it really is. But I wanted you to understand how these things come in a real life scenario, so that you can do your calculation. So we got a and b vector, and now we can find out the n vector, which we need to finish our calculation. How do we do this part? We need to do a cross b. Okay, can we do this? What should we write? The I, J, K. And here, these values, 0.39 and everything. So, point 1, 2, 8, 1, 4, 0, and over here we got minus 0.46, minus 0.082, and 0.0859. So you just copy things over, right? And in the cross product, what do? We fix a column, then multiply it the other way. Okay. So this is actually going to be, if you're going for I hat, what are the things we have? 0.1289 times 0.0859 minus these two things, right? So altogether this is going to be 3 minuses. That's one single minus. Minus times minus times minus. So that's 1 minus. And this is going to be 0.0820 times 0.1406. So that's for I. For J, we have a minus to start with. If you don't copy columns over, if you do that, then you don't have to change the sign. But let's say we do that. Over here, now we need to do the cross multiplication this way, 0.0391 times 0.0859, and then minus, thank you, minus these two. What's that? 0.0469 times 0.1406. And finally, K is what? K is these two multiplied minus multiplication of these two. So 0.03, I made a mistake right here, right? 0 is missing. So 0.391 times 0.0820, and then plus. Minus and then another minus. Thanks. Yeah, because there was a negative term over here. Okay, so right now what we got is a plus sign, and that's 0.0469 times 0.1289. Okay, so we got the new vector, this surface normal vector, written out like this, and we can simplify this. Since I got the calculator, let me just do it right away. Okay, that's 10028. So let me write that down somewhere. For this part, that's the result. So let me copy it over. And finally, for the I part, this is what we got. So altogether, is there a way that I can drag this? No. Probably I can't. Oh, yeah, got it. All right, so we got our n vector defined now. This is our n vector. Okay. Why did we need that? Because we need to do a L dot n. Can we do this bit? Yeah, it's easy. You multiply this thing with that, then do plus the j component and plus the k component. All right, you do the product and you add up all these products. So then you get that vector, you divide that by the magnitude of L, you divide it by the magnitude of n. Okay, I'm pretty much at the end of the class, so I'm not going to finish this over here. Let me leave it as homework for you guys. And in the next class, please let me know what's your answer so that we can cross-check. And I'll also try to finish this at home. And if our results don't match, we can then verify what went wrong. So let me write this down. Okay, so I'll save that. I don't need to save this. Any question about anything that we did over here? So if you actually understand the process, it's going to be the same thing for specular reflection. It's just that it's much more involving, because before even getting there, we need to calculate the reflection vector. And that means we need to do some vector addition, some multiplication over there. We developed a formula for that, how you come up with the R vector. Okay. So once you can calculate all these things, we can see how the color of each pixels. Right now we are calculating the color of a vertex, but we will talk about a scenario where we calculate the color of each pixel, because our ultimate target is this thing, to produce a result like this. So right now we are talking about the reflection of a vertex, not even a pixel, okay? Because it would have vertices like this. We are calculating the intensity right over here, but we haven't done anything about these things, which we need to figure out somehow. Okay? So that's it for this class. Please try to get it done before our Wednesday's class. Oh, actually, Wednesday we got a holiday, right? Yeah, we got a holiday. That's 21st February. So yeah, the next class, next Monday, we will discuss this topic again. But please finish the homework before you come to that class.
Yeah.